सभी को सप्रेम नमस्कार, ladies and gentlemen. On behalf of NEA, it is my pleasure to invite you all for the 80th CSIR Foundation Day celebrations at NAL. Before we begin, I request all of you to please put your mobile phones in silent mode till we conclude the program. Thank you. Today, on this occasion, we are privileged to have with us virtually Mr. Sunil Raina as the chief guest. He is the Managing Director of Collins Aerospace, Gurgaon. Welcome to the program, sir.
Thank you.
Also, it's my pleasure to invite Dr. G. Muthuselvan, Principal Scientist, Propulsion Division, CSIR NEL, who will be delivering the lecture in a short while from now. Welcome to the program, sir. We will start the program with a CSIR song.
भविष्य विज्ञान भारत का देखे सपने दृष्टाओं ने साकार किया उन सपनों को परिषद के सब सृष्टाओं ने परिषद के सब सृष्टाओं ने समय पर साधना करके अन्वेषण से आरंभ करके मन के संघर्षों को जगा के मौलिक धाराओं को गा के मौलिक धाराओं को गा के लेकर नवीन विचारों को सर्वजनों के सम्मुख जाए विश्व विजेता के बन लेकर विश्व विजेता के बन लेकर विज्ञान का विस्तार करेंगे विज्ञान का विस्तार करेंगे वैज्ञानिक औद्योगिक अनुसंधान करते हैं इस देश का कल्याण देश का कल्याण देश का कल्याण देश का कल्याण देश का कल्याण
I now request our director, Mr. Jitendra Jadhav, to formally welcome the guests and the gathering.
Good afternoon, Chief Guest Sri Sunil Raina, Dr. Muthuselvan, who is going to give us today's technology on lecture. Advisor Emmanuel Dr. Bhomik, and all my senior colleagues over here, and all awardees. Welcome to this CSIR 80th Foundation Day celebration. After a long time, almost after 2 years, we are sitting here. After a long time, because this auditorium was not at all operational because of the COVID restrictions. So I thought it's a good beginning that on the foundation day of CSIR will start functioning this auditorium. And all COVID norms have been followed. It's a good thing. CSIR being a first public funded research organization, which has started its journey from 1942. And today it's the 80th Foundation Day. So it's a very proud moment for all of us that India's first public funded research organization has come long way with 38 laboratories and so many units and lot of innovative and path-breaking technologies has gone to strategic, non-strategic, societal sectors. And yesterday, last night, DGCSI has told, apart from this, we did lot of intervention for the COVID-19 thing. So that is how that was a great pride for all of us to be with such an institute, and especially for me because I came from outside environment, and then slowly I become a member of this family. And as we said today, we have Sri Sunil Kumar. He is the managing director, Collins Sunil Raina, who is the managing director of Collins Aerospace. Welcome to you, sir, and it's our great honor for us to be, you are be here. And one thing I found from his biodata is he's an electronics engineer and he's also from the same university where I did electronics. So it's a coincidence, I believe. Okay, and it's nice to see you. And though we are meeting today in, virtually, we will meet personally soon.
Absolutely, sir. Thank you very much for welcoming me. Thanks a lot.
Welcome, welcome. So today we have one more thing is Mrs. Sridevi Jade, who has been appointed today as a head 4th year, and she is taking a charge of head 4th year to let us give a big hand. So she is so lucky that ACS Foundation is taking a charge of 4th year, and today she has taken a charge over it. Also, we must congratulate award which has gone as it's a very prestigious award, which is called it as CSIR Diamond Jubilee Technology Award. So it's a national award, not that only CSIR gives, so it only gives to the CSIR technology. It is like an open application award, where this particular award is made by the Government of India through CSIR for the commercialization of technologies which has succeeded right from the design stage and gone into the series production stage. So here today we have Ramesh Sundaram, Ravi Shankar, Kotresh, Baiju Varghese and team. It's very difficult to take names. They got today this award. It was a very difficult task from the laboratory technology to go into the flying platform. And as we know, we have made a fantastic progress in composite design development technology and for LCA, of course. And then there was a challenging task to get acquainted with the production rate, because LCAs are getting produced at 8 aircraft per year, but the components has to be produced 10 sets per year. Then only the aircraft can get produced 8 years. 10 also I am telling very less, but it is usually 1.5 years, 12 sets per year. But, and of course, you know, the breathing challenges or pitching challenges when we transfer the technologies to any private company. And there were a lot of challenges, like, first of all, I must tell you, this technology is supposed to be absorbed by none other than Hindustan Aeronautics, but they denied that we cannot fabricate this. And so we have to look for a private partner. And this award has been given between a private partner called Tata Aerospace Limited and CSIR for successful commercialization of LCA technology. So once again, congratulations to the team for the wonderful work. There are a lot of, we started from 15 June, there are a lot of achievements, so you should not forget. Entire Hansa team has done a marvelous work in last 2 years, 2.5 months, where we just roll out Hansa on 31st March 2021. And then we enter into these pandemic challenges. Then we thought when we will get open up. So 15 June we started working, and within 3 months, the whole aircraft has got airborne. So congratulations to the complete Hansa team, and the way they are worked, usually the way that they are worked day and night, it must be appreciable, whether it is QA, whether it is manufacturing, whether it is design, whether it is aircraft equipping, whether it is pilots, or whether it is flight test. All of them has synergically come. And as usually we used to tell, we have 70 number of letter of intents are already in place. But one more good news is, we have lot of people have approaches, and we are almost converting about 20 to 23 into purchase orders. So that is the greatest achievement of this. On top of this, there are a lot of work has been done in Saras Mark II and other things. But one important thing which we have taken a challenge is our high altitude platform. So today also, it's a very pet project of CSIR, and within a year we will be showing this high altitude of platform, a subscale version, flying on to the 15th August 2022 as the Azadi Kam also. So that is the biggest challenge. Today, exclusively we put one lecture on electric aircraft, because that is the future of the world. Because if you see now, any today's news, there are air taxis started, and they are going from point to point in the cities. It is basically the urban air mobility. So this is what people started working on urban air mobility, and slowly from the HAP, which is exclusive for pseudo satellites and all, we will be taking to the urban air mobility. The whole our thinking will take it to urban air mobility. So the challenges in urban air mobility is basically, we need a vertical takeoff and landing type of very, very reliable autopilot. Second one is, we have to take passengers into that, minimum 4 passengers. So it should work like a taxi. And then it should be electric, because nobody can afford that noise, nobody can afford any other thing. So it should be electric. So that is why we thought we will start beginning by converting Hansa propulsion based aircraft to the electric aircraft first. Understand what are the difficulties of converting propulsion based power plant to the electric power plant, and seamlessly go for this air taxi for urban air mobility. So that is what we are looking for. So as Hansa, all that thing will keep going into production slowly, but new designs also will start. So lot of divisions which are working on applied research, like SKD, MSD, then composite himself, structure, all this has to work for this, because it cannot be done if there is no technology available which are lightweight and all other special coatings, all these things technologies. Otherwise, it cannot be done. HAP is a totally different challenge, but air taxis, electric aircraft is a different challenge. So I urge all of you to start thinking in your divisions in that line of thinking. We have to take National Aerospace Laboratory towards complete air mobility and all that. Similarly, I will also tell Airport PI and all of your people that they should also start working along with us on artificial intelligence and some data science into that, because a lot of stuff has to be put it into this air mobility vehicle. So I will urge Airport PI to start also thinking into that line. With this, I think few words. I congratulate all the awardees today. I am proud to say that today we have 13 Indian patents, 4 foreign patents, 10 copyrights and 3 designs. It's a wonderful achievement. I think we should congratulate all of us. And thank you very much. And I welcome once again Sunil ji. We are looking for your very motivated speech soon. Thank you very much.
Thank you, sir. My pleasure to introduce our main speaker, Dr. Jubilee. He completed his Master of Engineering in the Department of Aeronautical Engineering from Madras Institute of Technology, Anna University. His ME project was on the reactive flow CFD simulation of hybrid rocket motor. He joined CSIR in the year 2008. He worked in the field of design and development of combustor and fuel injection systems for small gas turbine applications. He carried out several in-house and sponsored projects in the field of gas turbine combustion and fuel injection systems. He was awarded PhD from IIT Madras for his work on experimental study on lean blowout, acoustic oscillations, and emissions of modern gas turbine combustor in the year 2019. He published 4 international journal papers in peer-reviewed journals. He has presented 12 papers in national and international conferences. He has guided several MTech students for their project work. He also has received CSIR Young Scientist Award for the year 2019-20 for research and development of air-enriched combustion technology for small gas turbine engine applications. Presently, he is contributing to SARA's Mark II project in the design, development, and testing activity for fuel system. He is also interested in the development of vaporizer combustor for small gas turbine engine applications. May I now request Dr. G. to deliver the lecture, please.
Good afternoon, everyone. The topic of the presentation is about hybrid electric propulsion, a case study on CSIR NAL Hansa aircraft. So, as we all know, the present Hansa NG aircraft is having 38 HP Rotax IC engine, and which is having a cruise speed of around 190 km/h, and with the 85 liters of usable fuel, it is having a range and endurance of around 6 hours and 900 kilometers. So, in the present feasibility study, we are proposed to develop a hybrid electric power plant, and we have constructed a hybrid electric power plant using a rotary winding engines with the electrical motor and battery combination. And the performance of the aircraft in terms of range and endurance is calculated, and the overall torque is about that. So, this is the overview of the presentation. Initially, I will be discussing about the need of electrical and hybrid power plant, and I will be discussing about the recent development happened in the field of electrical and hybrid power plant. Then I will be discussing about the list of engines considered for this present construction of hybrid power plant. Then there was a requirement to develop a code to analyze the performance of the aircraft for a different proposed power plants. So I will be briefly discussing about the code developmental activity. Then I will be discussing about the details of the present case study with its results and concluding remarks. So here the conventional ICT power plant pivot is shown. So as we all know, the basic purpose of a power plant in an aircraft is to produce thrust. So here in the ICT power plant, the fuel stored in the aircraft, which will be the chemical energy of the fuel is converted into thermal energy in the engine. So the engine will be rotating the propeller, and it will be producing a force in the forward direction, that is called a thrust. So in the process of converting the fuel into the product, there is a combustion reaction is happening, and there is a heat release there, and this heat is used to do the work which is called thrust. So in the process of getting the energy out of the fuel, the combustion products are produced. So the basic combustion products are water vapor, carbon dioxide, carbon monoxide, unburned hydrocarbon fuel, and NOx. So this carbon monoxide and unburned hydrocarbon is represented as a degree of incomplete combustion. So all over the world, there are a lot of research is going on to suppress these levels, and the NOx is another greenhouse gas that also a lot of research is going to suppress. The major other product is the carbon dioxide. So as long as when we burn the fuel and then oxidize into the carbon dioxide, this product will be generated. We cannot remove this product with the use of unburned hydrocarbons. So, so this is giving a carbon footprint to the emissions and in the atmosphere. So that is the major push to go towards the electrical propulsion. So in electrical power plant system, the battery is replacing the fuel and it will be giving the energy to the motor. The motor will be running the propeller through the transmission system and which will be producing the torque. So here the CO2 footprint can be avoided. And the another advantage of this electrical propulsion is the noise level. Again, as we discussed, there is even and air is reacting. There is a heat release is happening, and there is a huge noise is produced. This noise needs to be giving a lot of challenges during takeoff and landing conditions. So this electrical propulsion system is another having advantage of suppressing this noise level also. In addition to these two big advantages, this electrical power plant is having additional benefits like the power won't deteriorate with respect to RGB, and the vibration and the maintenance are minimal because of electrical propulsion system. So this is given a good advantage of moving towards that. But already in the transport section, our electrical propulsion system is quite successful, and in the aviation field, already it is entering into the smaller flying activities like gliders. And even small aircraft also flying with respect of electrical power plant. But still, the major advantage of our conventional IC engine power plant is the two things I showed here. One is the high power to weight ratio, and another is the higher range and endurance. Why this is having still beneficial for IC engines? What was the issue with our electrical propellant with respect to this point will be discussed in the next slide. So here, the relative weight of power plant of both electrical and IC engine power plant is compared for an application of 1 kg force. If you want to generate at a speed of 150 km, the electrical power plant is weight is close to 12 kg. But in the case of ICG power plant, it is close to 2.3 kg. Out of 2.3, the engine weight will be 1.5 and the fuel weight will be 0.8. But in the case of electrical power plant, we are having a really efficient motor with a lesser weight, but the major weight occupied by is the battery weight, which is close to 11.5 kg. This shows the minimal energy density of this battery technology available today. So if you take a battery energy density available, it is close to 250 to 350. These numbers are keep on increasing. Lot of research is going on with this to further improve this number. But if we compare this with our petrol density, it is 50 times lesser. Our fuel is having an energy density of around 12,500 watt per kg. So in order to compare these two, we have to bring the efficiency of the machine also. The motor is having the efficiency around 90% and the engine is having the efficiency around 30% only. If you convert this, the power density of the electrical power plant per kg will be 6% of the power density of the IC engine power plant per kg of the fuel used. So this is the major limitation in the area of battery technology. This needs to be improved. Definitely in another sometime this number will be improved and this will be giving a bigger push to the electrical propellant system. So since there is the battery, then the power plant of electrical system is having higher weight penalty, the aircraft suitable for electrical application should be more efficient in terms of higher weight ratio, and it should have a minimal alert weight and the cruise speed will be minimum. So with the present battery technology, it is difficult to directly switch over from IC engine power plant to electrical power plant immediately. So we have to take a route of approaching this through a hybrid power plant, where we are having the advantage of using a high density fuel and a higher efficiency mission. So this is called a hybrid propulsion system, where both the power plants are taken and we will consider the overall power plant. So here both the power plant will be running parallelly and this is coming to the common transmission system that will be in giving this force. So this is called the parallel hybrid configuration, and many aircraft are flown using this configuration. In another 2 slides, I will be showing the aircraft using this configuration. And this is another configuration called a series hybrid electrical configuration, in which there is a generator center used with the IC engine. So this will be running IC engine generator combination will be running together and it will be producing electricity and that will be used to run the motor through transmission system to produce the thrust. So series configuration is having a infinite charging capacity, but the penalty is again the presence of generator. So if you take, I don't know if it's similar, okay, I'll explain here. If you take the 4 different stages of our mission profile of aircraft, these are the numbers for the class of aircraft. During the takeoff and flying, we need a very high power compared to the cruise and descent. So if we are operating both the power plant and we can able to do flying and takeoff, we can use the power for both the power plant. And during cruise stage, any one of the power plant can be used and it can meet the requirement of mission profile. So the overall requirement of the mission profile can be tailored according to the power availability in both the power plant system. So here are the some of these aircraft of all electric and the hybrids are shown. So the pistol is the one which is the all electrical aircraft, which is a 2-seater Raina aircraft with with the endurance of around 1 hour. It is flown in the year 2030. And there is one more aircraft called the extra 330 LV, which is also a 2-seater aircraft, which is having the endurance around 24 minutes, and it had a feature of higher rate of flying capacity. And later, these all-electric aircraft are converted to hybrid mode in order to increase the range and endurance. So this pistol is converted to 5-star mode, where the series configuration used with the Rotax 912 engine, and they use the motor around 150 kilowatt. So, and there is another inflator aircraft. This is initially started with the all-electric mode. Then it is converted into hybrid mode with the rotary ankle engine, and the maximum may take off 80,000 pounds with a single pilot capacity. And there are some more hybrid electrical power plant systems are used. And this is a Diamond D836, which is flown in the year 2017. This is a configuration of a series hybrid configuration with an electric motor of 60 kilowatt and the motor engine of around 30 kilowatt. And there was another aircraft called Eco engine, which is used a parallel configuration, which used a 912 Rotax engine. And there is another mechanism that the University of Cambridge, where the single pilot aircraft of strong aeronautical is used. This is a ultra-lightweight composite aircraft and using a series configuration. This configuration also demonstrated. So now the idea of using the existing IC engines, the hybrid electric power plant can be constituted. And so with that direction, we have carried out the list of IC engines available for this kind of classes. So as of now, there is no ready-made IC engines available for the hybrid application. But in near future, we can expect the engines for the hybrid applications. So the existing engines of classes only, which is converted for hybrid power plant systems. This is the important parameter, where the higher power to volume ratio is essential for hybrid power plant, in addition to the higher specific power. Because now in our hybrid propellant configuration, in addition to IC engine, we have to confine the motor and the battery configuration also. So this parameter is playing a major role in terms of constructing the hybrid power plant using an existing IC engine. So here again, if we compare a typical rotary and then IC engine. So this is a rotary engine and this is the IC engine. Almost the power classes are same, but the volume occupied by the piston engine is much higher compared to the rotary engine. So for the hybrid propellant system, the rotary engines are playing advantages over the reciprocating engine because of its higher power to volume ratio. So here another product of NAL is shown, the NAL 65 HP vehicle engine. In NAL, we have done the expertise in development of vehicle engine for the different power classes. The 55 HP vehicle engine was used to fly Nissan UAV, and the 65 HP vehicle engine is developed for punchy UAV application, and the another 30 HP engine was developed for a air-cooled concept. These are all the scientific shown for a vehicle engine of 55 HP, and this is used to construct this hybrid power plant. And the performance of this engine with respect to aircraft performance is considered in the present feasibility study. The overall idea is, so within the bracket, the the power of Hansa aircraft is shown. So during a takeoff, around 75 kilowatt power is required. So out of this 75, 49, around 48.5 kilowatt of power can be taken from the vehicle engine, and the balance will be taken from the electrical unit with the combination of battery and motor. If that in the direction, we have done a feasibility study. In addition to the existing vehicle engine, we have considered some more IC engines available, and the power class of around 50 to 65 HP engines are selected. And here, in addition to the rotary engine, we have shown some reciprocating engines of both the two-stroke and four-stroke. So here, again, you can see with respect to power to weight ratio and the power to volume ratio, rotary engines are showing a higher number compared to piston engines. And so based on this number, we have carried out the volumetric feasibility calculation. So we have taken the existing model of Nansen calling of a Hansa NG aircraft, and we have proposed the IC engine power plant and the electrical motor and battery are able to fix in that. Based on that, from two of the IC engines could not able to be fixed within the existing cowling. So these two engines are rejected and removed, and these are the five engines are used for the case calculation. So here the battery and the motor details are shown. So the Rotex engine is taken, the motor is taken. There is a two motors considering the present analysis. The 17 kg flex motor with the power of 50 kW is taken for hybrid configuration. And in the present feasibility study, we have considered a power plant of by all electric also. So there you need a higher motor. So the around 70 kilowatt motor is taken for all electric case, and the three different battery packs are chosen, and based on the power, then merit category, this is one of the battery packs, and one motor is chosen for each case of the. So here there is a requirement to develop a code to calculate the range and the endurance of the aircraft for a different power plant usage. So we have developed the code. Here the thrust power of the aircraft, propeller power, and the engine powers are equated together, and the overall range and endurance is calculated. So the approach is taking the propeller characteristics, engine power characteristics, and the aircraft parameters are taken into account. And in each stage of the mission profile, the distance covered by the aircraft and the time taken and the fuel flow consumption is calculated by following this equation, and the overall range and the endurance and total fuel consumed is calculated. So here these are all the performance plots are used inside the code to arrange the results. And here the major architecture of the code is shown here. So the operating conditions variation with respect to aircraft each stages, and the cruise altitude variation and densities are considered. And during the climb stage, the engine power is balanced with the propeller power, and with the propeller efficiency, thrust power, and other four forces of the aircraft is calculated. And during the climb stage, the four forces of aircraft is balanced first, then based on the thrust and thrust power and the engine power is calculated. So finally, the code will be giving the result for range, endurance, and total fuel consumption for the different configurations of hybrid power plant. So initially, the results of this code is compared with the available data of Hansa NG, and with the 3-4 iterations of fine tuning, the results of the code are very much matched with the available data. So this is given a confidence of using this code for a hybrid power plant application. So here, in order to implement the hybrid power plant, the component factor called electrification factor is taken into account. So here, the electrification factor is defined as power from the electrical unit to the total power available in the configuration. So nothing but the power of the electric power unit divided by the sum of electric power plus IC engine power. So with this definition, if you take a phi equals to 0 is the IC engine power plant case, and phi equals to 1 is the all electric case, and the phi varying from 0 to 1 is the hybrid case. So we made a provision to use this code and to investigate the effect of this electrification factor, and we have optimized the range and endurance with respect to this. And this is the overall schematic layout of the configuration. So in addition to the electric power plant and the mechanical power plant, we should be having the we should be able to develop the electronic controllers also. So that's the two controllers are required. One is the engine controller to vary the power settings with respect to the requirement, and there is the electrical motor controller required. So these two controllers will be communicating to the hybrid electric propulsion controller, and it will be controlled through the pilot. So this is the overall architecture of the steps configuration. So here, this is the major, the major outcome of this work. So the present hybrid power plant construction case, we have taken, this is the condition. The existing Hansa aircraft power plant weight is taken, which is close to 115 kg, and the fuel weight is close to 85 liters of fuel is around 65 kg. The total weight is around 180 kg. So in the hybrid power plant case, we kept the same weight of 180 kg, where the IC engine, motor, battery, and fuel weights are kept well within the 180 kg. So the power plant weight of the proposed hybrid unit and the IC engine unit was maintained constant, and the overall alloy weight was kept maintained constant. So the present Hansa engine is having alloy weight around 750 kg. So we have also maintained the same case. And the data plane, propeller characteristics, volumetric constraints, drag polar of the existing Hansa is maintained same. So now there is a different power requirement at a different stages of the mission profile. So the each proposed configuration will be meeting this power required with respect to the electrification factor. And here the volumetric feasibility study characteristics are shown. So and here the results are available. So as I already mentioned, there is a all electric case is also considered as a reference case, so that we can see with respect to hybrid how is our all electric case in terms of range and endurance of the present answer. So the present answer is having the range around 900 kilometers with the endurance of 6 hours by using the IC engine power plant. But the all electric case can give a range around 80 kilometers with the endurance of 24 minutes. So here during the takeoff and the climb itself, almost 50% of the energy is consumed. The balance 50 is used to do cruise and descent. So and since the energy availability was limited, we fixed the cruising altitude close to 4,000 feet, and the cruising speed is maintained close to 160 km/h. And in this three are the hybrid configuration where the three different engines are taken, and the balance energy will be supplied by the motor and the battery configuration, which is represented in terms of electrification factor value. So here we can see during the takeoff, the electrification factors are maintained 0.21 for the AR801 or the engine case, and these all five cases are representing different representation of electrification factor, which was moving from all electric case to different hybrid propulsion and hybrid configuration. So the battery energy was decreasing because of the higher power availability of each engine. And here the hybrid configuration considered by NL 65 axle engine is giving the range around 247 kilometers with the endurance of our 100 minutes. And during the takeoff and the flying state, higher energies are taken, so it is reflected as an electrification factor from the battery unit. And during the cruise, with the minimum support from electrical plants, this engine could be able to meet the requirement of cruising power requirement at the altitude of 6,000 feet with the cruising speed of 160 km/h. So, but the other available two engines, still the power levels are low. It was giving a lower range in endurance. And there was one more engine is taken, which is called a KPF 352 engine, which is developed in a Raina supertech engine, which is having a higher power capacity, and its cruising altitude is able to reach up to 8,000 feet, and its range is around 410 kilometers with the endurance of about 144 minutes. And here the endurance plot is shown for all the five cases. The other three cases can give an endurance around 36 minutes with a cruising altitude of 4,000 feet, and the hybrid power plant of using a nail 68 engine can meet around 100 minutes endurance with a cruising altitude up to 6,000 feet. And the other engines are, since the power was less, they are giving a lesser endurance compared to nail 68 engine. And this is the range distance. The nail 68 can able to reach up to 240 kilometers. And in addition to range and endurance calculation, we calculated a CO2 quantification per kilometer. So compared to the icing engine CO2 values, the hybrid power plant values are much lesser. And in addition to constructing this hybrid power plant, these are all the major challenges and technology challenges are there. That is identifying the compact electric motor and the higher power density pack and the thermal management of battery motor and generator configurations, and importantly this aeronautical certification. So from our case study, these are the conclusions we are making. It is possible to convert the existing aircraft as an all-electric or a hybrid unit, and the developed code was very much useful in order to estimate the preliminary performance of ANSA aircraft to get the range and endurance. And in all-electric case, with the single limitation of 4,000 feet, we could be able to get the endurance around 36 minutes. And with the proper selection of engine configuration, the cruising can reach up to 8,000 feet with the endurance from 1 to 3 hours. And the CSIR NLHP engine is a prominent contender to use this hybrid configuration. And the CO2 footprint of HEPS is reduced by 42% in comparison with the existing conventional ICE engine. Thank you.
Thank you, Dr. Mutsela, for a wonderful and enriching lecture on need-of-the-art technology. Now, it's my honor to introduce our chief guest, Mr. Sunil Raina. Sunil Raina is Managing Director for Collins Customer and Account Management in Indian subcontinent since year 2016. He leads Collins Aerospace operations and provides strategic direction for the company's initiatives in India. He is also responsible for strategic initiatives for the subcontinent, spanning both commercial and defense markets. He joined Rockwell Collins in Singapore in 2005 and has been involved in defining the strategies for the company's air transport, general aviation, and services businesses. Previously, he led the Rockwell Collins Commercial Systems Division in India and was successful in developing customer relationships and positioning the company as the preferred avionics partner for airlines in the Indian subcontinent. He has several industry and company awards to his credit. Raina is currently driving strategic partnerships with the Government of India, PSUs, and Indian companies to address offsets and the Make in India initiative. He is a graduate in electronics engineering from Pune University and has a postgraduate in management. He is an avid listener of Indian classic music and enjoys cooking during his free time. He lives in Gurgaon with his wife, Mrs. Madhu, and two sons, Ayush and Adiman. Over to you, sir, for your lecture.
Thank you very much. Thanks a lot for the introduction, Sangeet. To begin with, first of all, thank you, Mr. Jadhav and the team for giving me this opportunity today to present to the whole team on this important day for CSIR. It's honestly an honor to be here today and presenting to the gathering, which is obviously very learned. The engineering there are so many scientists around, doctors. So it's really a pleasure to address you today on this auspicious day. Thank you very much once again. What I wanted to do today very quickly was that I wanted to go ahead and give you what Collins Aerospace is globally and in India, how we are placed, just a little bit overview. And then obviously the most talked about subject in last 2 years, COVID, what we believe the industry is going towards and what is the impact of COVID. And obviously just to add the little bit of human side on that what Collins Aerospace has done during the COVID-19 and what challenges we faced. And in the end, I will quickly try to talk about the initiatives what Collins have taken to help get the industry back onto its feet quickly as early as possible, and then a little bit of future plans about India, what we are trying to do. I was glad that both Mr. Jadhav and Dr. Muthusalan, they talked about electrification, they talked about the autonomous, and those are the areas which obviously Collins is also looking into. And I think that will be a big piece going forward when you want to bring the industry back quickly into onto its feet. So before I go into Collins Aerospace, I wanted to talk about our parent organization. So it is Raytheon Technologies. 2020 January, two of the major groups, Raytheon company, which was purely the defense side of the business, and United Technologies, predominantly 75% commercial. They formed a company named Raytheon Technology. It was merger of equals, and now today we provide solutions systems for both commercial, military, and government customers worldwide. Under Raytheon, we have 4 business units. Collins Aerospace, obviously, I am part of that organization, but we also have Pratt & Whitney, which NAL is no stranger to because of the engines what we give there. And then we have RIS, which is Raytheon Intelligence and Space, and Raytheon Missile and Defense, which is RMD. If you see overall, the net sales for all the companies is literally balanced. So we are almost 50% divided today between commercial aerospace and the defense side. And Collins Aerospace, where I will like to dig deeper today, obviously coming from that organization, we have a net sales of $19 billion today. And what we do basically, Collins Aerospace is, so Collins Aerospace, basically, we are redefining the aerospace and defense with our innovation and disruptive technologies. That is our basic motto. And this motto of innovation, legacy of innovations and all that, it is not started today or 5 years back or 10 years back. This is what our core culture is. If I go to my next slide, this is what our legacy of innovation is. Whether you talk about the avionics and comm, it is the Collins who was the pioneer. Talk about electric systems, Mr. Sunstrand, environmental, Hamilton, Goodrich for landing system. So these were the pioneers at that time, and they thought differently, which today has helped the aviation industry to go to their next levels. And we have continued that legacy of innovation into our new cockpit systems, whether we are talking about the electric systems or the power control or landing nacelles, whether you're talking about the engines. So everywhere, our basic motto today is how to bring that innovation into those technologies. Quickly on the numbers, I just wanted to, obviously, I just said that we are a $19 billion net sales. But what is important on this chart, if you see, almost 4 billion, which is 25% of our net sales, goes back into the research and development. So that is very important. That is why I was just trying to allude that we are an innovative company. It's an engineering company, and we try to make those disruptive technologies which helps not only the aviation industry and also the mankind. Overall, about 70,000 people, equally divided between our aftermarket and OEMs. We are not a US organization anymore. 300 sites globally. Even in India, we have about 6 sites today, and a lot of engineering force globally, about 15,000 plus. Collins Aerospace, the way Raytheon is divided into 4 business units, Collins Aerospace in itself is divided into 6 major segments, which we call them strategic business units. Obviously, we touch almost every part of the aircraft today. So that is why it was very important for us to divide those different pieces into different areas like aerostructure, avionics, interiors, power and control. Mission is mostly the government or the defense side of the business, and then the mechanical. We'll go a little bit more deeper into each of them. Aerostructure, as the name suggests, it's more of composites, about the nacelle systems, the structures which we manufacture. We are doing a lot of innovation on that. So that is where the aerostructure comes into picture. Avionics, we have done a lot of business with NAL as well previously. It is mostly the avionics system, but with United Technology coming in, we are now into cabin management systems. We are into sensors and fire protection. I just wanted to touch a little bit extra on the information management. It is not only the data link piece there, but we have a big stake in the airports globally now. In India, we are working with Airport Authority of India. We are working with the private sector, and we are trying to see how we bring our latest technologies to the airport here, especially with the COVID in there, the lot of contactless is the way going forward. Interiors, name suggests itself, anything in the interior. Talk about the mats, or talk about the galleys, or talk about the lavatories, lighting, veneers, anything on the interiors part we are dealing today. Mechanical, we are into the landing system, actuations, propellers, control systems. Similarly, mission, it is more of critical towards the defense. It is not only the ground-based equipment, nav we sell there, but we are using our technologies from the other SBUs and giving it to the military platforms. We have a lot of business with the space side from this business unit, especially even with the ISRO here in India. We are working and giving them some solutions. We are working on the unmanned aircraft systems. We are not developing an unmanned aircraft, but more towards the complex systems which are required to fly those kind of aircrafts, and then the ejection seats for the military platforms. Going towards the controls, we are handling all the control, whether it is engine, electrical, air management, all the power and control systems are being run from the Windsor Lock Connect. So literally, if you see, we touch for the aviation industry, literally the moment you leave your house and by the time you reach back to your other side, the destination, we touch the lives of the passenger, aviation industry, airlines, customers, and end users, baggage, anything. We touch almost everything from ground zero to ground 100. So it's not only about sales. I just wanted to make sure that, okay, yes, we at the end, we want to have our products out there in the market. They are technology proven, reliable equipment, but then still we have dedicated customer services employees, about 10,000 of them, which are globally committed to give the support day in, day out. 6 labs, technical labs globally, which are handling 24/7 support. Any customer, whether it is in any remote corner of the world, any part of the day time, they have a response center number. You can go ahead and call them and they will make sure they will help you just in case you are outside those working hours for that country. And then apart from that, you have your own in-country service engineers. For us here in India, we have almost 6. These are some of the global locations for the manufacturing, MRO, then labs, customer support. So in India, I'm glad to say that we are about 6 to 7 sites which we are handling today. Especially the major workforce is in Bangalore and Hyderabad, but then we are handling it in the other pieces as well. So moving from globally, I just wanted to touch a little bit about the India. We started very early in this country, understanding that we need to have a presence here locally. And today we are proud to say that we are about 5,000 plus employees in India, mostly based out of Bangalore, which is our global manufacturing hub, and then the Hyderabad, which is our engineering hub at both Hyderabad and Bangalore. And then it is literally an end-to-end supply chain for the avionics, mission systems, and many other critical SBU technologies are being developed here. We do not only export to our own internal company, but we also supply directly to the other OEMs like Boeing, Airbus, Embraer. We send the equipment, whatever gets manufactured here, sometimes directly to the end customer as well. So we are one of the India's exporters of the aerospace products and also among the top exporters here. So we are doing what today is a big mantra for Make in India for long. We had started thinking about it a long back, and that's why we have a little bit of head up start there, especially with our competitors here. Just quick locations: Bangalore, Hyderabad, Delhi. They are the major places where our major offices are. But then apart from that, we have our technical people situation in Mumbai, down south in Cochin. So we are surrounded across India. But then Bangalore, as I explained, is mostly the manufacturing and engineering. the biggest chunk is out there. We are at the moment in Whitefield, but I will explain a little bit future plans in our further slides. Similarly, Hyderabad, we have the interiors, and we literally touch almost every SBU out of India. And it is not just the back end work what we are doing. We are coming out of patents out of India, almost 200 patents plus 200 plus patents now from the country, which have been filed. And then out of that, today, we have 10 projects which are being run and are being globally now delivered as well. So it's not just an engineering center to complete our back-end work. We are going ahead and helping globally, helping our international brethren to make sure that we are among the best, especially on the engineering side. So, okay, I think enough of Collins. I just wanted to move a little faster on that. Just a quick update on the COVID, because obviously everybody is concerned about that. We have not moved out, as we can see even in the conference hall today. Almost everyone is wearing their masks here, especially since I'm in the office and no one is around today. So I am excused of that, but otherwise the protocols we need to follow today are still be in mask and all that. So if you see in April, there was a forecast that by 2030, we will be about 5.6 billion passengers again. But in next 9 years, we will be still losing those 2 years, even less 7% what was expected growth when we started in 2019. Even today, by 2023, that is one more year, still one and a half years still to go. We are expecting that we will be to the 2019 level. And these are not Collins Aerospace numbers only. These are obviously a lot of research has been done across. It is obviously dependent on a lot of factors as well, how the border travel is removed, how the domestic increases, because you keep on hearing once a while that there is lockdown happening in this country, that country, and then between the countries they need to figure out how this travel will work. And based on those calculations, we still believe that by 2030 we will be losing at least 2 years just because of COVID. So COVID has impacted, I believe, our industry the maximum. So the most important thing is that it should not let feel us or make us let down our guards. We need to find ways how to come out of it and also move forward, especially how to bring this aviation industry back to its speed what we were before 2019. And I think that is what Collins is thinking, Collins is moving towards. And I was glad to hear the presentation from Doctor today that, okay, there is a lot of impetus on the electrical side, hybrid, how they want to move forward. Even in the director, he also, when he started his lecture, he also talked about that, the autonomous side. So I think we are also thinking on those lines, but I will go ahead and explain a little bit more. But before I go, I just wanted to give you a little bit of highlights what we did during the COVID-19 here in India, what initiatives and all that. Obviously, it was not only about the employees for us. The manufacturing, we had a manufacturing and it was global commitment. It was not only a commitment which we needed to give to India, what we are doing here. As I explained earlier, we were committed to give our equipment to the Airbuses, Boeings, and Embraers. So it was important for us to make sure that our factories are not closed for long. So with that, Government of India, Government of Karnataka, they helped us a lot to make sure that we were opened up on time. There was clear direction from the government how we need to do, what is the requirement, and then we had our own internal official requirements as well to make sure that our employees, contractors, whoever is visiting, they should be free. So there is a lot of work which was done on the background to make sure that at least we get the community safer as early as possible. So having said that, we used a lot of funds which we have, not only for the Indian side, but we got a lot of funds from our Raytheon Technologies to make sure we help India fight the COVID-19 crisis. Especially, I want to touch on the we donated about 4 mobile oxygen trucks, because as we all know that oxygen was in biggest demand those days, and it was supplying almost 270,000 gallons of oxygen by those 4 trucks directly to the hospital, connecting to their oxygen lines. So there was a lot of work done there. It was handed over to Red Cross, about a lot of protective equipment, oxygen concentrators, and not only that, I think with the help of our own team and doctors, I think we also set up a mobile hospital also during that time, just to make sure to reach to those people who were in need of the health facilities. There's some pictures handing over those oxy trucks to the Red Cross and all that stuff in the Palam side in Delhi. It helped a lot, and I think it was really appreciated by a lot of press and the government side. Vaccination drives, obviously, we went ahead and did vaccination drives in Karnataka. Since we have a bigger workforce there, you need people for that support. So we went ahead and did that as well. So I think, having said that, we all understand that COVID has definitely impacted us, and we as country have really struggled very hard to come out of it, and we are doing very well. There's no doubt in that. We are on the growth path back. So we need to figure out, get our industry also as quickly as possible back on the track. So just wanted to touch on some of the initiatives, what Collins is trying to do to help aviation come out a little faster out of what we have gone through. So first and foremost, we basically have got 6 initiatives today across Collins, and not only Collins, we are also using our other BUs, because we are in a unique place today where we can use each other's technologies and try to provide a solution for the industry. So connected ecosystem, I want to touch on this. We saw what important digital has done to our last 1.5 years to our lives, and even now today, just because I couldn't connect properly, so it just put everything on stop almost for a couple of minutes. So digital is very important. So what we are trying to do is we are trying to make our equipment smart, in the sense that you can pick up the data, can be collected, can be sent over the data link, and can be provided an end-to-end solution and service to the end customer. So there's a lot of focus on that, how these smart equipment, even if they have to talk to each other and try to move into that preventive health management systems, where you can predict, okay, here is the equipment, maybe there is an issue with that even before you go into the flight. So there are those kind of things which are going on at the moment. Obviously, electrified aircraft, we talked about it a lot today, and we are into it. There is no doubt. As Collins Aerospace, we have invested. We have obviously got some projects going on where the investments are coming. We are trying to see how together as industry we need to move forward and move to those goals what Dr. Muthu just now explained. Obviously, there's a lot of technical data there, but we are working on electrifying the aircraft as soon as possible. Autonomous, again, we talked about air taxis and all that. We are not manufacturing the aircraft side, but we are into the systems. Very clearly, we are a systems company. We are making those systems which will perform those complex tasks when the pilot is not on board. So there is a lot of work going on that front as well, and there is hopefully we should see an evolution to the autonomous flight soon with the kind of technologies we are trying to bring. Obviously, if you're moving that direction, you need to have structure sorted, and we are not only working on the external solution of the structure, we are also trying to find out the interior, how we can use those advanced materials and the latest manufacturing techniques, state-of-art manufacturing facilities to bring those weights less and make sure that industry is benefited. Then on the defense side, obviously, when you are in war, which no one of us wants. But then when you are in war, you want to make sure that one message is relayed to literally every place wherever we need to go. So there is no confusion when you are in that battle space. So there is a cross-domain connectivity happening, and we are working on that connectivity as well. And then in the end, obviously, we are a company which today has we are fortunate to have different systems. So we are trying to see how we can cross those traditional system boundaries and get that mission enhancing system for the aircraft, not only aircraft, like we are working towards the digital security side, where if there is a requirement for a nuclear plant to provide that security digitally, so we work on those systems, or whether it's a rail system, aviation, air transport, controller, ATCs, so we can provide those security systems to that also, because digital, obviously, we understand needs to be very secure before we go into these mission critical functions. So basically, if we are trying to do these 6 things, so as I explained, we are in that position. We are in a unique position to do that, but we are basing this whole initiative on 4 pillars. First and foremost, obviously, is the collaboration. Unless we have people internal, the communities, the customers working together, or the industry also. So that is why I think, like what we are doing today, it is important for us to share notes, make sure what we are trying to do with each other, and then it makes easier for us, because the collaboration, that's why I said, is very, very important if we want to make some of these initiatives work together. Again, R&D, no doubt about that. We, as I explained, almost 25% of our net sale goes back into the R&D. So we are pioneering on that. But obviously, we are also getting investments from the government, defense sectors, industry partners. So we are working on that to see how we can bring those sustainable technologies. I talked about smart products. Basically, they need to be more reliable and more smarter. So that is what the idea is. Basically making a product digitally enabled, so that even if you have to go ahead and upgrade the product in future, how can we do that software enabled? How can we work more, not removing those products out of the aircraft? So we are moving in those direction. And then the last, which is obviously very important, the environmental side, because we saw how much havoc can be created in the last 2 years, what has happened, the whole disruption. So we have to be mindful of how we can make our future generation secure. So there is a lot of impetus on the environmental. Whatever we are doing, we make sure that it is not affecting our environment in general. So out of these 4 pillars, I just wanted to give you a little bit an explanation how we do the goals. And I just picked up on the environmental side, because I know we are already almost towards the end, but I just wanted to let you know what goals we are trying to set for one piece of environmental. By 2015 till today, we have already reduced so much, but our goals for 2025 is literally reduced emissions for in-house greenhouse emissions, almost literally implement 100% water waste implementation. Nothing gets out to the environment, so we are trying to get that out 100%, reducing the waste, landfill, all that. Every 1% reduction is a lot of investment. So it may seem a little less, but then it is a lot of investment on our part to make sure that the humanity should not suffer. So just wanted to give you one example how we make those goals for our future. Just the last couple of slides talking about the future and what happened during COVID, like this picture. I wanted to talk about this contactless. We were one of the first ones when this, after COVID, the airports started opening. We were one of those first. We started working with the airports and got the contactless working. So the way this thing works is you will go, once you go in to the kiosk, you can have your mobile just pointed towards that, and you will get all the controls what is on the kiosk on your phone. So basically you can you don't need to touch the kiosk as well, and you can work from your phone. So we have got that already working in some of the airports globally. So the moment you enter the land at the airport until the time you board, you do not have to touch anything if you are if you have all these smart systems installed on that airport. So we brought that technology, so that was very has been accepted globally for a lot of industry. We are working with the airport authorities here. We are working with the private airport service providers to explain them how this will work. And I think there is a lot of interaction going on, and I think interest as well to see how we can bring those state-of-art things to the country. Then for us here in India, we are building an factory near the Aero Park in Bangalore, which is near the airport. The first phase will start in the first quarter of next year, and the plan is to move the whole factory there slowly. That is what the idea is. But then we already have started, the work is already going on, and hopefully we should be starting that in the first quarter next year. It is already important just to know that we have got so much work going on with these in these factories now, that place, even though it has not come up yet, but we already have got the business to make sure that that will start working finally. So we have to move faster on that front. And then even on the engineering side, we are trying to consolidate all these 3-4 sites which we have in Bangalore to at one place near Hebel, which will be one Collins Aerospace facility where we want to consolidate. So a lot of investment going, a lot of labs are being built in India. So we as Collins Aerospace are definitely invested here, and we want to make sure to work closely with the government and see how we can bring this this sector back to growth, especially with our connected aviation ecosystem for the Indian aviation. And then obviously, as Raytheon, I explained earlier that we have critical infrastructure, digital security for them, which is end-to-end, whether it is a nuclear plant, whether it is a space mission, whether it is an you want to cover some boundaries, so we can provide those critical end-to-end solutions for any missions. And then the last one, but not the least, there is a lot of technologies now which were previously commercial flight decks, but are now being used for military use. And we are trying to see how we can utilize those plans, especially in India as well. So I think that is it from me. I know I went very fast. A lot of things to be cleared, but let me know if you have any questions. I am here. I can share. If I can get an answer straight away, I can. But then maybe if need be, I can get back through the team who have approached me, and I can get back some answers in case there are more questions, or in case there is somebody who needs more interaction. My details are there, so you can always connect me directly as well. Thank you very much, and thanks once again, Mr. Jadhav, for giving me this opportunity.
Thank you, sir, for giving an insight to Collins Aerospace activities and its initiatives. Hope NAL and Collins Aerospace will collaborate for the ongoing and future aerospace programs.
I request our chief guest to formally launch the Icast website. Information Center for Aerospace Science and Technology, Icast Web Portal, is redesigned to provide single-window access to several web-based information services to the CSIR NAL community. The major web services integrated are eJournals Gateway to access online journals, WebOPAC to search physical holdings of the library, digital library platforms, Shodh Pawan, a discovery platform for scholarly literature, Scientist Profiling Service to capture SCI publication metrics of NAL, Prakash to capture internal technical literature, NAL Open Access Repository and off-campus access to resources on anytime, anywhere access, and research support services.
On behalf of CSIR, NAL, IP and BDG team, I have pleasure to inform you that today we are awarding 39 inventors for their significant contribution in enhancing the IP portfolio of CSIR NAL. It is proud moment for all of us that CSIR NAL has contributed 155 inventions to CSIR. Of this, more than 100, more precisely 105 are granted in India and 37 in abroad and 12 are pending. On business front, 26 inventions have been licensed to 66 industries, generating a revenue of 632 lakhs. For today's event, there are a total of 30 Indian patents, 4 foreign patents, and 10 copyrights and 3 designs, covering new materials, coatings, composite manufacturing techniques, and new engineering products. I request the awardees to come to dais on announcement of their name. I request our director to please present the certificates. An Indian patent on a process for obtaining recoverable deformations in shape memory polymers, SMP, has been awarded to Dr. Sandhya Rao, Principal Scientist, ACD. Srimati Revati, Senior Technical Officer, ACD. Srimati Kavita Varlish Rao, Senior Technical Officer, ACD. Dr. Shailaja Srihari, Senior Principal Scientist, SID. Sri M. Chandin Murugan, Senior Technical Officer, ACD. An Indian patent for a shape memory alloy SMS-based composite repair device for repairing the composites have been awarded to Dr. Sunil Kumar, Senior Principal Scientist, ALD. The G.M. Kamalakannan, Chief Scientist, ALD. And Dr. B. Saji, Chief Scientist, UAAB. Dr. R.V. Lakshmi, Principal Scientist, SCD, has been awarded with an Indian patent on corrosion inhibiting salt gel coating composition for coating metallic surfaces, and an Australian patent, a hybrid multi-layer solar selective coating for high temperature solar thermal applications, and a process for the preparation thereof.
And an Indian patent for an improved binary pressure sensitive paint, along with Dr. A. Satyanarayanan, Principal Scientist, EAD, and Dr. L. Venkatakrishnan, Chief Scientist, EAD. Dr. S.T. Aruna, Senior Principal Scientist, SCD, has been awarded 2 patents for corrosion inhibiting salt gel coating composition for coating metallic surfaces, and an improved metal composite coating reinforced with volcanic rock particles, along with Sri M. Muniprakash, Technical Officer, SCD, and Srimati S. Lata, Senior Technical Officer, SCD. Dr. Ramesh Sundaram, Chief Scientist, ACD, has been awarded 2 Indian patents for a system and method for visualizing real-time resin flow front in resin infusion technology for manufacturing composites, and a process for manufacturing co-cured composite structures and product manufacture thereof, along with Sri Kundan Kumar Verma, Principal Scientist, ACD, Sri Kailash Singh, Senior Technical Officer, ACD, Sri Gaddikari Kotrish, Chief Scientist, ACD, and Sri B.L. Dinesh, Senior Technical Officer, ACD.
An Indian patent has been awarded to Sri Nitesh Gupta, Senior Principal Scientist, ACD, and Sri N.J. Agastine, Principal Scientist, ACD, along with Dr. Ramesh Sundaram for a system and method for visualizing real-time resin programs in resin infusion technology for manufacturing composites. An Indian patent is awarded to Shri E. Rajesh, Senior Principal, Senior Scientist, Propulsion, for pitching mechanism for diffuser blades of centrifugal compressor. Dr. Harish Bachidia, Chief Scientist, ACD, has been awarded with 3 patents, 2 Indian patent and 1 Australian patent for an improved process for the fabrication of nanoporous microstructure on glass and the production for produced data. A modified solar selective coating having high level stability and a process for the preparation data, and a hybrid multi-layer solar selective coating for high temperature solar thermal applications and a process for the preparation data. Dr. James Balaraju, Senior Principal Scientist, ACD, has been awarded 3 patents, 1 Indian, 1 Australian, and 1 US patent for a process for the preparation of corrosion-resistant steel anodized coatings on aluminum alloy. Dr. P.K. Panda, Chief Scientist, Material Science Division, and Venadu Sahu, Principal Scientist, Material Science Division, have been awarded an Indian patent for a process for the preparation of lead-free barium calcium tin titanate and fibers. Dr. Soumendra Jana, Chief Scientist, Propulsion, has been awarded with an Indian patent for improved electromagnetic actuator. Dr. Manju Nundam, Senior Principal Scientist, ASISD, and Sri G. Shamsundar Dage, SPO 3 ASISD, have been awarded 2 copyrights for integrated mutation analysis tool, RegStore, and intelligent knowledge database software tool. Dr. G. Kumar, Principal Scientist, AAG, has been awarded copyrights for integrated Drishti remote display software for IGA Airport and unique multiple online data communication tool and multiple code-based anti-preparation deprotect software for Drishti and web publishing software along with the Sri Mahesh V, Principal Scientist, ASIS. Dr. Hema Singh, Senior Principal Scientist, GM, has been awarded with a copyright for CSIR NAL active cancellation of probing in phase arrays post. Dr. Suresh Kumar Karthik, Senior Principal Scientist, FMCD, and Dr. B. Parthasarthi Naidu, Senior Principal Scientist, FMCD, have been awarded the copyright for data acquisition software for EBS flight experiments. Dr. Balamati Chaudhary, Principal Scientist, CEM, and Dr. Ravindranath U. Nair, Chief Scientist, CEM, have been awarded with the copyright for SPARKS, Stealth Platform Asymptotic Radar Cross-Section Software.
I now request Dr. M. Manju Prasad, Advisor Works and Services and Head KTMD, to propose vote of thanks.
Good evening. First of all, I would like to congratulate all the IPR awardees on this happy occasion of CSIR Foundation Day. And I would like to thank our director for having, handed over the awardees with all the certificates. So I would like to thank our chief guest of the day, Sri Sunil Raina, MD Collins Aerospace, for having kindly accepted to deliver the CSIR Foundation Day lecture and taking us through the interesting works both in India and globally, and also sharing the work what they have done for the containment of or the societal requirements during the COVID period. I would like to thank our internal speaker who for delivering the NIL business lecture on electric hybrid propulsion and sharing some of the interesting facts and figures and also some of the results what they got during the preliminary studies carried out at NIL. I would like to thank all a function of this sort cannot be arranged without the active cooperation and support from various divisions. I would like to thank all the divisions, principally the ASISP team, the HLS team, electrical team, the EBU team, the director's office, and also my own KTMD team for actively contributed for the success of this function. Once again, I would like to thank all the participants of this function and all the invitees who have participated in this program, both physically in the auditorium as well as who have watched the program through the webcasting. Thank you all. Thank you.
Thank you, sir. We will conclude the program with the national anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल गंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Thank you.
Thank you, sir.
Thank you very much. Thanks a lot. Have a great evening. Bye.